Today, we'll start our discussion on the next topic in the scope of the present course, CVL 443, that is cylindrical shell structures, as part of the second component of the present course, which is based on industrial structures, while the first component of the course was based on pre-stressed concrete structures. The discussion on cylindrical shell structures that are one of the most commonly encountered industrial structures in the civil engineering industry will be focused on axisymmetrically loaded thin cylindrical shells, since most of the cylindrical shell structures that are implemented in the industry may be classified or identified as axisymmetrically loaded thin cylindrical shells. Commencing our discussion on the next topic in the scope of the present course, that is cylindrical shell structures, as part of the second component of the course that is based on industrial structures, we will begin our discussion with an introduction to cylindrical shell structures and their applications in the civil engineering industry that are wide-ranging over a variety of industrial structures that will be introduced in the present topic. Further, we'll continue with an introduction to the general theory of shells, that is the most fundamental theory or mathematical formulation of the structural behavior of shell structures. Our objective in the course of the present discussion will be to begin from the most general theory of shells, that is the fundamentals of the general shell structures, to the development of the mathematical formulations of the internal actions in an axisymmetrically loaded thin cylindrical shell, since most of the cylindrical shell structures that are implemented in the civil engineering industry can be identified or classified as thin cylindrical shells subjected to axisymmetric loading. Hence, starting from the first principles of the fundamental theory of general shell elements, we will formulate the mathematical relationships for the internal actions, that is, the internal forces and moments in an axisymmetrically loaded thin cylindrical shell, relating the internal actions to the internal displacements in case of thin cylindrical shells subjected to axisymmetric loading. Proceeding to the introduction of cylindrical shell structures as one of the most commonly encountered industrial structures. An example that is most commonly found in the civil engineering industry of the cylindrical shell structure is a cylindrical water tank, in which a cylindrical shell is provided as the structural system for resisting the external loads. In case of the cylindrical water tank, the external loads that are predominant or governing the structural response of the cylindrical water tank are the hydrostatic forces or the hydrostatic loading. It is worthwhile to mention that a cylindrical water tank can be identified or classified as a cylindrical shell structure with a thin cylindrical shell subjected to axisymmetric loading, that is exerted by the hydrostatic pressure acting on the cylindrical shell. There are a number of other examples or instances of cylindrical shell structures or simply cylindrical shells in the civil engineering industry, and the variety of applications that the cylindrical shells find in the civil engineering industry range over a broad spectrum of industrial structures. For example, overhead or underground cylindrical water reservoirs, chimneys, silos. There are several other examples of applications for cylindrical shell structures as mechanical engineering structures or aeronautical structures or marine or naval structures. For example, cylindrical shells are implemented in the fabrication of pressure vessels, for example, boilers, which is an example of the mechanical engineering industry, aircrafts, the structural system of an aircraft is essentially a cylindrical shell for most of the part of the body of the aircraft or aeroplane, which is an example of the aeronautical or aviation industry. Submarines, in which a large part of the body of the submarine is a cylindrical shell, is an example of the application of cylindrical shell in the naval or marine industry as a naval structure or a marine structure. With that brief introduction to the broad-ranging applications of cylindrical shell structures in the industrial field, let us proceed to the discussion of the general theory of shells, that is the fundamental theory of general shell element, and the most obvious or natural starting point of the introduction to the general theory of shells is the definition of a shell. Well, a shell is defined as a surface with a relatively small thickness, say denoted as T, that is generated by rotating one or two planes about two different axes. For example, O1, O1 and O2, O2, as illustrated in these two figures here. Well, focusing on the second figure here, the figure illustrates a general shell element or a shell surface with a small thickness T that is generated by rotating one plane, that is illustrated by the green dashed dotted line, about the axis of rotation O1, O1, with the radius of rotation R1, that is termed as the radius of curvature, or one of the radii of curvature of the shell surface thus generated, as well as rotating a second plane that is shown or displayed as the red dashed dotted line about the axis of rotation O2, O2, with the radius of rotation as R2 about the axis O2, thus generating the complete shell surface by rotating the plane with the about the axis O2 with the radius R2, that is the second radii of curvature for the shell surface thus generated. It is worthwhile to note here that the two radii R1 and R2, that are the radii of rotation of the two planes about the two axes of rotation O1 and O2 and are termed as the radii of curvature R1 and R2 of the shell surface thus generated may be both finite and non-zero, where or while one of the radii can be positive and finite, while the other can be positive or negative, in which case, that is, in the second case, where the second radius of curvature that is used to generate the shell surface is negative, the shell surface that is generated will have a double curvature. We will present such a shell surface with a double curvature shortly. However, the shell surface that is presented in this figure is a shell that has a single curvature, or the radii of curvature that are both finite and positive. In conclusion, one should mention third possibility where one of the radii of curvature, for example R1, at which the first plane is rotated about the axis of rotation O1 and O1, is finite and positive, while the second radii of curvature R2 at which the second plane, that is in this special case a hypothetical plane rotated about an imaginary or hypothetical axis of rotation O2 with the radius of rotation R2 as infinite, thus generating the special case of a cylindrical shell surface, as one can observe from this first figure on the left hand side. The shell surface that is generated by rotating one plane, that is plane represented by the dashed dot green line, about the axis of rotation O1, O1, with the radius of rotation R1, that is the first radius of curvature of the shell surface thus generated, while the other radius of rotation, that is the second radius of rotation R2 of the second plane, that is rotated about the hypothetical axis O2, O2, in case of a cylindrical shell surface, is infinity. Therefore, to conclude the discussion on this slide, a cylindrical shell or a cylindrical shell surface with a finite thickness T is generated by rotating one plane about an axis of rotation O1, O1, with the radius R1, that is the radius of rotation R1, termed as the radius of curvature of the cylindrical shell, while the second radius of curvature R2, that is the hypothetical the radius about which the second hypothetical plane is rotated about the hypothetical axis of rotation O2, O2, is infinity. And a common example of cylindrical shells or cylindrical shell surface, other than the examples previously mentioned, for example, cylindrical water tanks, water reservoirs, chimneys, silos, pressure vessels, etc., is the shell roof system illustrated in the figure on the left hand side, which is also known in architectural terms as jack arch roof, which implements a series of cylindrical shells or cylindrical shell surfaces generated by rotating each surface, that is generated by rotating plane about an axis of rotation O1 and O1 with the radius of rotation R1, that is the only finite radius of curvature of the shell, while the other radius of curvature of the cylindrical shells or cylindrical shell elements are infinity or non-finite in case of a cylindrical shell such as the one shown in this figure. Continuing our discussion on the introduction to cylindrical shell structures and in general shell structures as well as the general theory of shells, it is worthwhile to add that, as mentioned in the context of the previous slide, in case one of the radii of rotation, that is the radii of curvature of the shell surface that is generated by rotating a plane about an axis of rotation O1, O1, for example, the radius 1 of curvature, radius of curvature R1 is negative or less than 0, as illustrated in this figure, while the other radius of curvature, that is the radius 2 of curvature, denoted as R2, which is the radius of rotation of the other plane about the second axis of rotation, O2, O2, for generating the shell surface is finite and positive, then in this special case, shell surface with the double curvature is generated. A physical example of a general shell with a double curvature is a horse saddle, schematic of which can be visualized in this figure on the present slide, wherein the radius of rotation of the first plane, represented by dashed dot green lines, about the first axis of rotation, that is O1, O1, is negative or less than 0, while the radius of rotation of the second plane, depicted by the dashed dotted red lines, termed as the second radius of curvature or radius of curvature R2, that is used for rotating the second plane about the second axis of rotation O2, O2, is positive, thus resulting in a shell surface with a thickness T that is much smaller than either of the two radii R1 and or R2 of the curvature the shell in terms of the absolute value or the magnitude. That has a double curvature as depicted in this figure. Proceeding to the general theory of shells, that is the fundamental theory of shell elements, in order to derive the general state of forces or stresses in a general shell element from the first principles of the theory of shells, the general state of forces or internal actions in a differential shell element, such as the one shown in the second figure, that is the figure in the lower half of the present slide, for a differential shell element with a single curvature for simplicity. That has differential dimensions dx and dy, and thus the general shell element displayed in the figure is termed as a differential shell element due to the differential dimensions dx and dy of the shell element with reference to the choice of the Cartesian coordinate system that is selected for formulating the general state of internal actions or forces in the differential shell element, and illustrated in this figure as the Cartesian coordinates x, y, which are the two coordinate axes in the plane of the shell element, while the Cartesian coordinate z, that is the z-axis, is pointing out of the plane of the differential shell element, with the origin of the three Cartesian coordinate axes x, y, and z at the origin point O that is located at the centroid of the differential shell element shown in the figure. It may be noted that the origin O of the Cartesian coordinate frame of reference, as well as the Cartesian coordinate axis x, y, that are the Cartesian coordinate axis in the plane of the shell element, and intersect at the origin O, lie in the mid-surface of the shell element, that is the mid thickness of the shell element. Therefore, based on the differential shell element illustrated in the figure on the lower half of the present slide, with the choice of the Cartesian coordinate axis x, y and z selected for formulating the general state of forces or internal actions in the differential shell element, the general state of internal actions in the differential shell element with differential dimensions dx and dy in the limit dx and dy tending to 0 as implied by the prefix differential for the dimensions dx and dy of the differential shell element can be classified into two fundamentally different types of internal actions. One, in-plane or membrane actions that act in the plane of the shell and are illustrated in this figure, and two, the out of plane or the plate actions that are the internal actions acting out of the plane of the shell as suggested by the respective terms, that is in plane or membrane actions acting in the plane of the shell, and two, the out of plane or the plane act or the plate actions acting out of the plane of the shell. Elaborating on the in-plane or the membrane actions that act in the plane of the shell with reference to the choice of the Cartesian coordinate system of axes x, y and z, there are four in-plane actions or membrane actions acting on the differential shell element, that is the internal axial force in x, which in general varies along the spatial coordinates and acts on the x face of the differential shell element, that is the face of the differential shell element normal or perpendicular or orthogonal to the x-axis in the selected choice of Cartesian coordinate system of axes. since the internal action Nx, that is the internal in-plane axial force Nx, in general varies along the spatial coordinate x, the in-plane axial force Nx acting on the negative x face and the in-plane axial force Nx acting on the positive x face of the differential shell element are different in the sense that the in-plane axial force acting on the positive x face of the differential shell element will be incremented or will have an increment that is equal to the partial derivative of the in-plane axial force Nx with respect to the spatial coordinate x times the differential dimension dx of the differential shell element. In other words, the in-plane axial force Nx acting on the positive x face of the differential shell element will have a differential increment that is equal to del nx by dx times dx due to the spatial variation of the in-plane axial force Nx in general along the x coordinate. Now here there is a need to define the sign convention as well as the notation. In general, the notation capital N subscript ij denotes an in-plane internal action N acting on the I face of the differential shell element, for example, the x face of the differential shell element, in which case I will be x, and subscript j signifying the direction of the internal action. And the internal action N denoted as capital N subscript ij is considered to be positive if acting on the positive I face, for example, Nx for n subscript x acting on the positive x face and acting in the positive j direction. That is, for example, positive x direction, as in case of nx. In case I and j are both the same, that is, I and j are both x or y coordinates, then the second subscript j is omitted for brevity or for sake of briefness. The second subscript j is omitted or dropped from the notation in case both I and j are the same, as in case of the in-plane axial force Nx, which acts on the positive x face and is considered to be positive when acting in the positive x direction, and thus j is equal to I, that is, the subscripts I and j are both the same as x. Hence, adopting the sign convention just explain wherein an internal action n denoted as n subscript ij is considered to be positive if acting on the positive I face, for example, the x face or the y face, where a positive I face is defined as the face of the differential shell element perpendicular, normal or orthogonal to the positive I axis, for example x or y axis, and the internal action n subscript ij acts in the positive j direction, where j may assume the values of x or y, or j may be x or y axis. In case the subscript j is equal to the subscript I, as in case for the internal action and x acting on the positive x face of the differential shell element and in the positive x direction, thus resulting in both j and I being x coordinate. The second subscript j is dropped, or maybe dropped or omitted for sake of briefness. Hence, the second in-plane internal action is that needs to be considered for the differential shell element illustrated in this figure is the in-plane axial force N subscript Y acting on the Y face of the differential shell element, that is, the face of the differential shell element perpendicular, normal or orthogonal to the y-axis, and since the in-plane axial force Ny, based on the adopted sign convention just defined, acts on the y face of the differential shell element and is therefore considered to be positive when acting on the y face of the differential shell element and in the positive y direction. The subscript, the second subscript j, is equal to the first subscript I in the designated sign convention and notation, and hence the second subscript j is dropped for brevity, and the in-plane axial force Ny, that is n subscript y, where the notation n signifies the in-plane axial force, while the subscript y signifies that the in-plane axial force n subscript y acts on the positive y face of the differential shell element and acts in the positive y direction when considered positive. And as in case of the in-plane axial force Nx, the in-plane axial force Ny in general varies along the spatial coordinate y, or varies spatially, and in order to account for the spatial variation of the in-plane axial force Ny along the coordinate y, the differential term is included in the magnitude of the in-plane axial force Ny acting on the positive y face. In other words, if the in-plane axial force Ny acting on the negative y face thus considered positive when acting in the negative y direction, has the magnitude n subscript y, then the in-plane axial force acting on the positive y face, considered positive when acting in the positive y direction, has a magnitude Ny plus differential term that is given as the product of the partial derivative of ny with respect to the y coordinate times the differential dimension dy. Continuing along the similar line of reasoning based on the adopted sign convention and notation, there are two other in-plane or membrane actions that act in the plane of the shell, which are the in-plane shear forces nxy and nyx. Based on the sign convention and the notation that we just defined, nxy is the in-plane shear force acting on the positive x face of the differential shell element, considered positive when acting in the positive y direction. Since the subscript j in the adopted sign convention in case of the in-plane shear force nxy is different, that is, the subscript j is y and is different from the subscript I, which is x, in case of the in-plane shear force nxy. Both the subscripts I and j, or x and y respectively, are retained for clarity. And as in case of the other in-plane or membrane actions, the in-plane shear force nxy also varies spatially, and based on the sign convention that is defined earlier, if nxy is the in-plane shear force acting on the negative x face and thus considered positive if acting in the negative y direction, then the in-plane shear force acting on the positive x face, that is nxy, considered positive when acting in the positive y direction, in general has an increment and is given by the nxy plus the partial derivative of nxy with respect to the spatial coordinate x times the differential dimension dx. In other words, the in-plane shear force acting on the positive x face of the differential shell element and hence considered positive when acting in the positive y direction is equal to the in-plane shear force NXY acting on the negative x face, considered positive when acting in the negative y direction, plus a differential term that is given by the product of the partial derivative of the in-plane shear force NXY with respect to the spatial coordinate x times the differential dimension dx as illustrated in the figure. As a recap, to refresh your memory, the sign convention that we are following is that an internal action denoted as capital N subscript ij is considered positive if acting on the positive I face, where the I face is the face of the differential shell element perpendicular normal or orthogonal to the x-axis or the y-axis as applicable, and the internal action Nij is acting in the positive j direction, where j may assume the values x or y. That is, the internal action Nij is acting along the positive x or y directions respectively. Hence, continuing with our definition of the internal in-plane or membrane actions acting in the plane of the shell, the fourth internal in-plane or membrane action is the in-plane shear force NYX. NYX, that is the internal in-plane shear force acting in the plane of the shell, which, based on the adopted sign convention defined earlier, is considered positive when acting on the positive y face and acting in the positive x direction, since I assumes the value of y and j assumes the value of x in case of the internal in-plane shear force NYX. And as in case of the other internal in-plane shear force NXY, NYX, that is the internal in-plane shear force acting on the y face in the x direction, varies spatially along the spatial coordinates, as one can note from this figure. The in-plane shear force NYX considered positive when acting on the positive y face of the differential shell element in the positive x direction is incremented by a differential term, hence to account for the spatial variation of the internal in-plane shear force Nyx along the spatial coordinates, if Nyx is the internal shear force acting on the negative y face of the shell, considered positive when acting in the negative x direction, then based on the sign convention and the notation that we have defined and following the same sign convention, the in-plane shear force Nyx acting on the positive y face of the differential shell element when acting in the positive x direction that is the internal in-plane shear force Nyx acting on the positive y face of the differential shell element considered positive when acting in the positive x direction as depicted by this green half arrow. Is obtained by adding a differential term to the in-plane shear force Nyx acting on the negative y face, where the differential term is given as the product of the partial derivative of the in-plane shear force Nxy with respect to the spatial coordinate y times the differential dimension dx of the differential shell element. Thus concluding our discussion on the general state of the in-plane or membrane actions, that is, the internal actions that act in the plane of the shell. Recall that, as mentioned earlier, there is another type of internal action or another class or category of internal actions that act out of the plane of the shell, which will be discussed in the next slide. However, the general state of internal actions depicted in this figure on the present slide, based on the sign convention and the notation that we defined in our discussion in the context of the present slide, summarize the general state of internal actions that act in the plane of the shell. Continuing our discussion on the general theory of shells, that is illustrating the general state of internal actions or forces and moments in a differential shell element defined as a shell element with differential dimensions dx and dy in the limit where dx and dy both tend to 0, the second category or class of internal actions in a differential shell element of a general shell is the outer plane actions or the plate actions, which are defined as the internal actions in a general shell element acting out of the plane of the shell element, as the name or the term outer plane or plate action suggests. And the general state of outer plane or plate actions that act out of the plane of a differential shell element are illustrated in this figure for a differential shell element with differential dimensions dx and dy with reference to the same choice of Cartesian coordinate axis x, y and z that was selected for illustrating the in-plane or the membrane actions in a general shell element. However, as the term outer plane or plate actions implies the outer plane or plane actions that comprise of the internal actions acting out of the plane of the differential shell element consist of the following. One, the bending moment mx acting on the positive x face of the differential shell element, that is the face of the differential shell element which is perpendicular, orthogonal or normal to the x-axis, with the moment vector mx pointing in the positive y direction. Based on the sign convention that we defined earlier for the in-plane or the membrane actions in the differential shell element, Sign convention for the internal out of plane or plate actions, that is the internal actions acting out of the plane of the differential shell element, which are illustrated in this figure, is essentially the same. And the notation of the outer plane or plate actions, that is the internal actions in the differential shell element acting out of the plane of the shell element, is also essentially similar in a sense to that for the in-plane or the membrane actions. For example, a bending moment acting on the positive x phase, such as m subscript x, is considered positive. When acting on the positive x phase with the moment vector mx pointing in the positive y direction. On the other hand, the bending moment mx acting on the negative x phase, that is the x phase of the differential shell element, perpendicular or normal or orthogonal to the negative x axis, is considered positive. When the moment vector mx acts in the negative y direction, and in general the internal outer plane or plate action, for example, the out of plane bending moment mx acting out of the plane of the differential shell element varies spatially along the spatial coordinates. And in order to account for the spatial variation of the internal outer plane or plate actions in the differential shell element, for example, the bending moment mx acting on the positive x phase, or in general the x phase of the differential shell element, the bending moment is incremented by a differential quantity given as the partial derivative of the bending moment mx with respect to the spatial coordinate x times the differential dimension dx of the differential shell element. In other words, the bending moment acting on the positive x face of the differential shell element mx is equal to the bending moment mx acting on the negative x face plus a differential term that is equal to the product of the partial derivative of the bending moment mx with respect to the x-axis times the differential dimension dx of the shell element. Continuing further with the same sign convention and notation, the next internal out of plane or plate action that needs to be considered in the statical equilibrium of the differential shell element illustrated in this figure is the bending moment my, and the bending moment my based on the sign convention and notation that we defined earlier is the bending moment acting on the y face of the differential shell element illustrated in this figure and is considered positive when acting on the positive y face with the moment vector pointing in the positive x direction. However, the bending moment my when acting on the negative y face is considered positive if the moment vector my is pointing in the negative x direction. And as in case of the internal in-plane or membrane actions, the notation follows the same line of reasoning, and internal out of plane action, say Mij, for example, is considered positive if acting on the positive I face, for example, mx is considered positive if acting on the positive x face, with the moment vector pointing in the positive j direction. For example, the internal outer plane bending moment mx is considered positive when acting on the positive x face, with the moment vector mx acting in the positive y direction, and the subscript j is avoided for the sake of brevity, or the second subscript in the notation is dropped for the sake of briefness in case there is no conflict between the notations. And for simplicity, therefore, the torsional moments Tx, Ty, and the shear forces that act out of the plane of the differential shell element Qx and Qy, rather Qx and Qy, are assigned a different notation than the bending moments in order to highlight the difference in the nature of the torsional moments Tx and Ty and the outer plane shear forces Qx and Qy from the bending moments mx and my as well as each other. Hence, based on the sign convention and the notation just defined for the outer plane internal actions or the plate actions in a differential shell element shown in this figure, the next type of the internal outer plane or plate action that can exist for a differential shell element of a general shell shown in this figure is the out of plane shear force denoted as Qx acting on the positive x face, considered positive when acting in the positive z direction. And the counterpart of the internal outer plane shear force acting on the negative x face denoted as Qx, is considered positive when acting on the negative x phase in the negative z direction. Whereas in case of all other internal actions, whether internal in-plane or membrane actions that were discussed in the previous slide, or the internal outer plane or plate actions, for example, the bending moments mx and my, discussed in the context of the present slide and the present figure, the internal outer plane shear force Qx also varies spatially along the spatial coordinates x, and in order to account for the spatial variation of the internal outer plane shear force Qx along the spatial coordinate x, the differential term that is given as the partial derivative of the internal outer plane shear force Qx with respect to x times the differential dimension x dx of the differential shell element is added to the differential to the in-plane rather the outer plane internal shear force Qx. In other words, the internal outer plane shear force acting on the positive x phase, considered positive when acting in the positive z direction, is obtained as the internal outer plane shear force acting on the negative x phase, considered positive when acting in the negative z direction, plus a differential term equal to the partial derivative of the outer plane internal shear force Qx with respect to x plus times rather the differential dimension of the differential shell element. Similarly, there is a internal outer plane shear force Qy acting on the Y phase, that is considered positive. When acting on the positive Y phase, and in the positive Z direction, and the internal outer plane shear force Qy acting on the positive Y phase is obtained by adding or incrementing the internal outer plane shear force acting on the negative Y phase, denoted as Qy, considered positive when acting in the negative Z direction. With a differential term that accounts for the spatial variation of the internal outer plane shear force Qy with respect to the spatial coordinate y, and is given as the partial derivative of the internal outer plane shear force Qy with respect to y times the differential dimension dy. Further, in addition to the bending moments mx, my, and the shear forces qx, qy that act out of the plane of the differential shell element and are thus termed as plate actions. There are two torsional moments that can exist. In addition to the bending moments mx, my, and the outer plane shear forces qx and qy, and these torsional moments, for purposes of clarity, in order to avoid any conflict, in the symbols or notations. With the other internal outer plane or plate actions are denoted as Tx and Ty, where the notation T denotes that the moment is a torsional moment, while the subscript X or Y denote that the torsional moment T, X or Ty is acting about the positive x-axis or the positive y-axis respectively. Once again, in order to refresh your memory on the sign convention and notation that we are following to define the general state of internal actions in a differential shell element, is that the notation M, T or Q signifies or represents the nature of the internal action. For example, the notation M denotes bending moment, while the notation T denotes torsional moment, and the notation Q denotes an out of plane shear force. And as in case of the in plane or the membrane actions acting in the plane of the differential shell element, the notation signifies the nature of the internal action. For example, in case of the in plane or the internal membrane actions, the notation N represents the in plane axial force or the in plane shear force, while in case of the out of plane or the plate actions that act out of the plane of the differential shell element, the notation M denotes bending moment, while the notation T denotes torsional moment, and the notation Q denotes the out of plane internal shear force. And the subscripts I and j in the notation for the internal outer plane of plate actions bear the same interpretation or have the same interpretation as the subscripts I and j in case of the internal in-plane or membrane actions that were defined in the sign convention and the notation presented earlier. To elaborate, a notation Mij or Tij or Qij denoting the internal outer plane bending moment or torsional moment or outer plane shear force respectively are considered positive if acting along the positive I face that is on the positive I face in the positive j direction. For example, the bending moment mx acting on the positive x face of the differential shell element is considered positive if the moment vector of the bending moment mx is pointing in the positive y direction, and the bending moment my is considered positive if acting on the positive y face with the moment vector pointing in the positive x direction, wherein I and j can assume the values of x or y as applicable. Similarly, the torsional moment Tx is considered positive when acting on the positive x face with the moment vector pointing in the positive x direction, while the torsional moment Ty is considered positive when acting on the positive y face with the moment vector pointing in the positive y direction. Following the same line of reasoning, the outer plane shear force Qx is considered positive when acting on the positive x face with the shear force in acting in the positive z direction. On the other hand, the shear force Qx is considered positive when acting on the negative x face with the shear force acting in the negative z direction. Further, the other shear force, that is the out of plane shear force Qy, is considered positive when acting in the positive on the positive x face, positive y face rather, in the positive y direction, positive z direction rather. On the other hand, the outer plane shear force Qy is considered positive when acting on the negative y face in the negative z direction. And in general, all these internal outer plane or plate actions vary spatially along the spatial coordinates x and y in the differential shell element, and hence the differential terms are required to model the spatial variation of these internal outer plane or plate actions mx, my, qx, qy, tx, and ty. Also, the second subscript in the designated notation, for example, mij, tij, and qij, the subscript j is dropped since there is no conflict between the symbols m, t, and q representing the bending moments, torsional moments, and the out of plane shear forces, respectively. To summarize, therefore, the general state of internal actions in a differential shell element, such as the one shown in this figure or with the outer plane or plate actions, and the differential element shown in the previous slide with the internal in-plane or the membrane actions, in summary, there are 4 in-plane or membrane actions that act internally which are nx, ny, nxy, and nyx, as depicted in the figure on the previous slide for the differential element, illustrating the internal in-plane or membrane actions on a differential shell element. While there are 6 in-plane, outer plane or plate actions denoted as mx, my, qx, qy, tx, and ty that are depicted on the figure shown in the present slide for a differential shell element of a general shell. Hence, there are 10 unknown variables, that is the 4 internal in-plane or membrane actions, nx, ny, nxy, and nyx, plus 6 outer plane or plate actions, mx, my, qx, qy, tx, and ty, resulting in 10 unknown internal actions totally, or 10 unknown variables, while as in case of any solid body or solid, we have 6 equations from the consideration of statical equilibrium, and the 6 equations may be summarized as the 3 force equilibrium equations, sigma Fi equal to 0, where I, the subscript, can assume the values of the coordinate axes x, y, and z, implying that there are 3 force equilibrium equations, sigma Fx equal to 0, sigma Fy equal to 0, and sigma Fz equal to 0, that need to be satisfied for the statical equilibrium of the differential shell element or any solid for that matter. In addition, there are 3 moment equilibrium equations, sigma mi equal to 0, where the subscript I can assume the values of the coordinate axes x, y, and z, thus implying that there are 3 moment equilibrium equations, sigma mx equal to 0, sigma my equal to 0, and sigma mz equal to 0, based on the consideration of moment equilibrium about the x, y, and z axis of the differential shell element or the solid body, hence providing 6 statical equilibrium equations. And as apparent, the number of unknown internal actions, which are 10 in number, or the unknown variables, number of unknown variables, are less than the equations available from consideration of statical equilibrium, which are 6 in number. That is, the number of unknown variables or the unknown internal actions, which are 10 in number, is greater than the number of equations that are available from the statical force and moment equilibrium considerations of the solid or the differential shell element, the problem is statically indeterminate. In other words, the solution of the internal actions in the differential shell element is statically indeterminate. Concluding our discussion on the general theory of shells and the solution of the general state of forces or stresses that exist in a differential shell element as internal actions that were presented in the previous slide, the differential shell element, that is the general shell element displayed in the previous two slides with differential dimensions dx and dy in the limit dx and dy tending to 0, is in equilibrium under the action of 6 out of plane or plate actions and 4 in plane or membrane actions, thus resulting in a total of 10 unknown internal actions, which are either forces, that is axial forces and shear forces, or moments, that is bending moments or torsional moments, as well as external loads or external loading that may be characterized for the differential shell element with differential dimensions dx and dy tending to 0, subjected to concentrated external loads px, py and pz acting at the mid surface of the differential shell element as illustrated in the figure of the differential shell element presented in the previous two slides, and acting through the origin of the local element coordinates based on the choice of the Cartesian coordinate system selected to represent the local coordinates of the differential shell element. And as a result of the external loads Px, Py and Pz acting in the three orthogonal directions along the three coordinate axes x, y and z with reference to the local element coordinates, that is the local Cartesian coordinate axis for the differential element that is selected as the frame of reference, generate the internal actions. Hence, since the number of the unknown variables consisting of the four in-plane or membrane internal actions, that is nx, ny, nxy, and nyx, plus the 6 out of plane or plate internal actions, that is mx, my, qx, qy, tx, and ty, based on the notation and the sign convention defined earlier, thus resulting in a total of 10 unknown internal actions or 10 unknown variables while the number of equations that are available for solving the 10 unknown internal actions or unknown variables are only 6 from the consideration of the statical equilibrium of the differential shell element, which are the 3 force equilibrium equations sigma fx, sigma fy, and sigma fz equal to 0, and the 3 moment equilibrium equations for the differential shell element, that is sigma mx, sigma my, and sigma mz equal to 0. And as the number of unknown variables or the unknown internal actions that are 10 in number are more than the number of equations available from the considerations of statical equilibrium of this differential shell element, the solution of the general state of internal actions in a general differential shell element is statically indeterminate. Hence, one can conclude that the solution of the unknown internal actions in a general differential shell element that was considered in the discussion of the general theory of shells is statically indeterminate and requires the application of kinematics or compatibility of displacements. Further, as in case of any statically indeterminate problem, for example, the problem of solving the bending moments and shear forces in a statically indeterminate frame structure as an analogy, one needs to also apply the stress-strain relationships or the constitutive laws for the material of the structure in order to relate the displacements to the internal actions and thus solve for the unknown internal actions and the unknown internal displacements. In summary, the solution of the statically indeterminate internal actions, including the in-plane or membrane actions as well as the outer plane or plate actions in the general differential shell element considered for discussion of the general theory of shells in the previous two slides, requires the application of the three fundamental concepts of structural analysis, as in case of any statically indeterminate problem, which are: 1. Statical equilibrium, providing the 6 equations from the consideration of the statical equilibrium of the differential shell element in 3 dimensions, or for the 3 coordinate axes x, y and z. 2. Kinematics or compatibility of displacements that need to be considered, since the solution of the unknown internal actions that are 10 in number in case of the general differential shell element is therefore statically indeterminate, hence requiring the application of kinematics or the fundamental of the compatibility of displacements. And 3, the constitutive material laws or the stress strain relationships of the material of construction of the differential shell element, in order to relate the internal actions to the displacements, and thus resulting in sufficient number of equations to solve for the unknown internal actions, including the in-plane or the membrane internal actions and the out of plane or the plate internal actions that are generated in the general differential shell element due to the application of the external loads Px, Py and Pz, illustrated in the figure for the differential shell element in the previous two slides. Before proceeding to the application of all the 3 fundamentals or concepts of structural analysis, that is statical equilibrium, kinematics or compatibility of displacements, and stress strain relationships or the material constitutive laws, let us first explore if the statical equilibrium equations among the internal actions, that is, the 10 internal actions that can exist in a general differential shell element, can be solved by themselves, that is, independently, by applying or implementing some simplifying assumptions that are not only realistic but also reasonable and therefore do not result in any significant loss of accuracy. In other words, before we proceed to set up the larger problem of solving the equations from all the three fundamentals or concepts of structural analysis, that is, before attempting to apply the additional fundamental concepts of kinematics or compatibility of displacements and the stress-strain relationship, let us first explore the possibility of solving for the 10 unknown internal actions, that is, the 4 in-plane or membrane internal actions, Nx, Ny, Nxy, and Nyx, and the 6 outer plane or plate internal actions, that is Mx, My, Qx, Qy, and Tx, Ty, based on the considerations of statical equilibrium alone, although we understand that strictly or rigorously speaking, the problem of solving the 10 unknown internal actions is in fact statically indeterminate, as we have already established based on our discussion of the general theory of shells by examining the statical equilibrium of a differential general shell element illustrated in the figure on the previous 2 slides. Hence, for sake of argument or discussion, just to explore the possibility of solving for the 10 unknown internal actions in the general differential shell element based on statical equilibrium considerations alone, by making some simplifying assumptions or implementing some simplifying idealizations that are both realistic reasonable and thus do not result in any significant loss of accuracy. Which are also practically admissible from the point of view of the physical behavior of the differential shell element and general shells in the practice. For example, in case of most practical shell structures that are constructed in the industry, for example, the cylindrical water tanks with the cylindrical shell structure, the cylindrical pressure vessels with cylindrical shells as the primary structural system, have a thin shell. That is, in most of the practical applications of shells in the civil engineering industry or other industries, the shell is thin or may be idealized as a thin shell. Since most of the practical shell structures that are encountered in the field have a thin shell, and based on this practical reality, one can assume that the shell in the shell structure that is constructed in practice is a thin shell, assumption that is commonly referred to as the thin shell assumption. And the thin shell assumption that is based on the idealization that the shell is thin is valid if and only if the thickness of the shell is much less than the radius of curvature R1 as well as the radius of curvature R2. In other words, assumption A that idealizes the shell to be a thin shell is valid if and only if the thickness T of the shell is negligible in comparison to either of the two radii of curvature R1 and R2 as represented mathematically by equation number 1. As a result, of the shell being thin, that is, the thin shell assumption, the flexural rigidity or the stiffness of the shell can be neglected. In other words, the assumption A, termed as the thin shell assumption, that is based on the idealization that the shell is thin, which is valid in case the thickness T of the shell is much smaller than either of the two radii of curvature R1 and R2, mathematical condition represented by equation 1, which is the necessary and sufficient condition for the thin shell assumption to be realistic and accurate, in which case the flexural rigidity or the bending stiffness of the shell can be considered to be negligible, and as a consequence the thin shell that satisfies the necessary and sufficient condition given by equation 1 to qualify as a thin shell is unable to resist any bending and torsional moments acting out of the plane of the shell element. The physical interpretation of this inference is that the thin shell, or in case of a shell that is thin and satisfies the necessary and sufficient condition given by equation 1 to qualify as a thin shell, has negligible flexural rigidity or bending stiffness. For example, a sheet of paper as in practical instance or physical example of a thin shell. A sheet of paper, for example, the A4 size sheet of paper or the printer paper, is a realistic example of a thin shell, since the thickness of the paper or the shell is negligible in comparison to either of the two radii of curvature in case the paper is or shell is bent, molded in the form of a shell structure. In case of such thin shells which satisfy the assumption that the shell is thin, the thin shell, for example, the sheet of paper, is unable to resist any out of plane bending or torsional moments and as a consequence, the external moments and the external forces, that is, the external loads acting on a thin shell, are resisted primarily by in-plane or membrane actions, simply because a thin shell is unable to resist out-of-plane actions such as out-of-plane bending moments and torsional moments due to the negligible flexural rigidity or bending stiffness of the thin shells. In conclusion, a shell that satisfies the assumption of thin shells fulfills the necessary and sufficient mathematical condition given by equation 1 to qualify as a thin shell, acts as a membrane under the action of external loads, since the external loads in case of such a thin shell are resisted primarily by in-plane or membrane actions, as the thin shell cannot resist any out-of-plane bending or torsional moments due to the negligible flexural rigidity or bending stiffness of the thin shell, thus constituting the mathematical proof for the membrane theory of shells, which states that the external loads acting on a thin shell are resisted primarily by in-plane or membrane internal actions. In a sense, the membrane theory of shells implies that a thin shell that qualifies the necessary and sufficient condition given by equation 1 for the thin shell assumption to be valid, acts as a membrane. Continuing our discussion on the general theory of shells and the solution of the unknown internal actions, including the internal in-plane or membrane actions Nx and y, Nxy and Nyx, as well as the unknown internal out-of-plane actions or plate actions Mx, My Qx, Qy, and Tx and Ty recall that we had implemented a simplifying assumption or idealization that the shell in the shell structure is thin. That is assumption A presented in the previous slide, which idealizes the shell in the shell structure of interest to be a thin shell, and thus is termed as the thin shell assumption. The thin shell assumption, presented as the simplifying assumption number A in the previous slide, is valid if and only if the thickness T of the shell is negligible in comparison to the two radii of curvature of the shell, that is R1 and R2, a mathematical condition that is the sufficient and necessary condition for the thin shell assumption to be reasonable and valid as expressed by equation number 1 presented in the previous slide. Further, recall that the thin shell assumption implies that the thin shell acts as a membrane. Since the flexural stiffness or the bending stiffness in case of a thin shell that fulfills the necessary and sufficient condition to qualify as a thin shell expressed by equation number 1 on the previous slide, if and only if the external loads are resisted primarily by the membrane actions in the thin shell. In other words, the thin shell acts as a membrane if and only if the external loads are resisted primarily by membrane actions in the thin shell. A hypothesis that is termed as the membrane theory of shells, which states that a thin shell resists the external loads primarily by in-plane or membrane actions if and only if the thickness of the shell T is negligible in comparison to the radii of curvature R1 and R2 of the shell. Which is the necessary and sufficient condition for the shell to qualify as a thin shell and therefore a membrane. As expressed by equation number 1 presented in the previous slide. The mathematical proof of the membrane theory of shells for a thin shell just stated can be simply formulated by considering the statical equilibrium of the differential shell element of a general shell presented in the previous or earlier slides, assuming that the shell in the differential shell element is a thin shell and satisfies the necessary and sufficient condition expressed by equation number 1 presented in the previous slide to qualify as a thin shell. The sign convention and notation that will be employed for the mathematical proof of the membrane theory of shells for thin shells just stated is the same as the one that was presented in the earlier discussion on the general theory of shells. In other words, the sign convention and notation that will be used for mathematically deriving or proving the membrane theory of shells just stated is the same as the sign convention and notation that was presented and discussed in the context of the general theory of shells and the statical equilibrium of the general differential shell element as discussed in the previous slides. The sign convention and notation can be read and understood once again from the description provided in the present slide, which formally presents the sign convention and notation that is adopted and followed for the internal actions in the general differential shell element for the purposes of refreshing your memory on the sign convention and notation that was explained in detail in the earlier discussion on the general theory of shells. Hence, please take a few moments to read the guidelines for the sign convention and notation of the internal actions that have been adopted and followed for presenting and discussing the general theory of shells and the solution of the internal actions in a general differential shell element that are reproduced in the present slide as a recap to refresh your memory. Before we proceed to the mathematical proof of the membrane theory of shells for a thin shell. Continuing our discussion on the general theory of shells and the solution of the unknown internal actions in a general differential shell element of differential dimensions dx and dy presented in the figure in one of the earlier slides. Applying the assumption of thin shells, that is, the thin shell assumption as commonly referred to the solution of the unknown internal actions, that is, the internal in-plane or membrane actions nx, ny, nxy, and nyx, and the unknown internal outer-plane actions or plate actions mx, my, qx, qy, tx, and ty, as depicted in the figure of the general differential shell element presented in an earlier slide. Can be obtained by employing the theory that the thin shell acts as a membrane. Provided that the hypothesis that the flexural stiffness or bending stiffness of a thin shell is negligible, and hence the external loads acting on a thin shell element are resisted primarily by membrane actions. In case such a hypothesis that a thin shell acts as a membrane, thus implying that the flexural rigidity or the bending stiffness of the thin shell is negligible or zero, and hence the external loads acting on the thin shell element have to be resisted primarily by membrane actions. Is correct. And the mathematical proof of the hypothesis that a thin shell acts as a membrane if and only if the assumption of the shell being thin is reasonable, realistic, and valid in the sense that the assumption does not result in any significant loss of accuracy in determining the unknown internal actions in the differential shell element, that is, the shell element satisfies or fulfills the necessary and sufficient condition to qualify as a thin shell expressed by question number 1 presented in one of the earlier slides, which states that the necessary and sufficient condition for a shell to qualify as a thin shell is that the thickness T of the shell is negligible, much less than either of the two radii of curvature, R1 and R2 of the shell. In which case, the thin shell assumption, that is assumption number A, that has been implemented to simplify the solution of the unknown internal actions of the differential shell element discussed in the earlier slides will be realistic and valid, and consequently the hypothesis that the thin shell acts as a membrane, since the flexural rigidity or bending stiffness of a thin shell is negligible or zero, and hence the external loads are resisted primarily by membrane actions in the thin shell. The physical explanation of the hypothesis that a thin shell acts as a membrane, for which the mathematical proof will be presented shortly, is that a thin shell or a membrane is unable to resist any out of plane or plate actions, that is, any out of plane bending moments or torsional moments due to the negligible flexural rigidity or bending stiffness of the thin shell, as in case of sheet of printer paper that is appropriate example of a thin shell, since a sheet of printer paper has negligible flexural rigidity or bending stiffness, and therefore is unable to resist any out of plane internal actions such as out of plane bending moments or torsional moments. Hence, equation 1, that is the necessary and sufficient condition for a shell to qualify as a thin shell, implies that the bending moments mx, my, and the torsional moments tx, ty that act out of the plane of the thin shell are all negligible or almost equal to 0, as expressed by equation number 2, simply because the flexural stiffness or the bending stiffness of a thin shell is negligible, provided the thin shell qualifies the necessary and sufficient condition for a thin shell, that is, the thickness of the thin shell is negligible in comparison to either of the two radii of the curvature. Question 2, that implies that the out of plane internal actions, that is the out of plane bending moment mx, my, and the out of plane torsional moment tx, ty are all negligible or 0, results in the simplification of the statically indeterminate problem of solving for the unknown internal actions in the general differential shell element presented in the figures in the earlier slides, since equation 2 implies that the bending moments mx and my acting out of the plane of the thin shell, and the torsional moments tx and ty also acting out of the plane of the thin shell, both or all have to vanish due to the inability of the thin shell to resist any out of plane internal actions, simply because the flexural rigidity or the bending stiffness of the thin shell is negligible or zero. Hence, the thin shell assumption reduces the number of unknown internal actions in the differential general shell element presented in the earlier slides to 6 unknown internal actions or unknown variables from the original 10 unknown internal actions or unknown variables, as 4 of the unknown internal actions, namely the bending moments mx, my and the torsional moments tx, ty have been reduced to zero or can be considered to have vanished because of the thin shell assumption and the hypothesis that the thin shell resists the external loads primarily by membrane actions. Since the outer plane internal actions mx, my, tx and ty have all been reduced to a negligible or zero value as expressed by equation number 2, the solution of the general state of internal actions in a general differential shell element presented in the figures in the earlier slides is considerably simplified, as we now have only 6 unknown internal actions or 6 unknown variables, that is nx, and y, nxy and nx and yx, as well as the outer plane shear forces qx and qy that remain to be solved. And since the number of statical equilibrium equations that we have available from the considerations of the statical equilibrium of the general differential shell element presented in the figures in the earlier slides is 6, that is 3 equations based on the statical force equilibrium and 3 equations based on the statical moment equilibrium of the differential shell element. It appears that the solution of the non-zero internal actions, that is nx and y, nxy and nyx, and qx and qy may be statically determinate, as there are 6 equations that are available from the consideration of statical equilibrium of the differential shell element. And exactly 6 unknown internal actions that are remaining to be solved after the application of the thin shell assumption. Therefore, proceeding to apply the statical equilibrium equations one by one in order to solve for the 6 remaining unknown internal actions nx and y, nxy and yx, qx and qy, we first apply the moment equilibrium equation that seems to be the simplest for purposes of application or calculation, that is the moment equilibrium equation about the x-axis based on the choice of the Cartesian coordinate axis as the frame of reference, illustrated for the differential shell element presented in the previous slides. And the moment equilibrium equation about the x-axis, that is sigma mxx, considering anti-clockwise moments to be positive, equal to 0, that is the summation of the bending moments and torsional moments about the x-axis equal to 0 results in a 0 value of the out of plane shear force Qy as expressed by equation number 3. It is worthwhile to mention here that the summation of the bending moments about the x-axis due to the internal actions as well as the external loads acting on the differential shell element illustrated in the figures in the previous slides is elaborated here. And the higher order terms of the differential quantities dx and dy, that is dx square and dy square, and higher order terms of dx and dy have been neglected in the formulation of the moment equilibrium equation about the x-axis for the differential shell element. Similarly, the moment equilibrium equation about the y-axis of the general differential shell element illustrated in one of the previous slides results in a 0 value of the outer plane shear force Qx neglecting the higher order terms of dx and dy, since the differential dimensions dx and dy tend to 0, and in the limit that dx and dy tend to 0, the higher order terms of dx and dy, such as dx square and dy square, as well as the higher order terms, all tend to 0, thus resulting in a 0 value of the outer plane shear force Qx as expressed by equation number 4. In physical terms, the physical explanation of equations 3 and 4, that is the physical interpretation of the mathematical derivations for equations 3 and 4, is that since the outer plane bending moments mx and my acting on the general differential shell element illustrated in the previous slides are both negligible or equal to 0, due to the negligible flexural stiffness or bending stiffness of the thin shell by virtue of the thin shell assumption. The associated shear forces Qy and Qx that are associated with the bending moments Mx and My are also reduced to 0. In other words, since the bending moments Mx and My acting on the idealized thin shell in the general differential shell element vanished or reduced to 0 due to the negligible flexural rigidity or bending stiffness of the thin shell. The outer plane shear forces Qx and Qy also vanish or reduce to 0. In case of the differential shell element being thin, that is, provided the thin shell assumption is realistic and valid, and the hypothesis that thin shell resists the external loads primarily by membrane actions or acts primarily as a membrane is true. Proceeding further with the mathematical proof of the hypothesis that a thin shell acts as a membrane and thus resists the external loads primarily by membrane actions due to the negligible flexural stiffness or bending stiffness of the thin shell. The application of the third moment equilibrium equation, that is sigma mzz equal to 0, that is the summation of the bending moments about the z-axis equal to 0 in order to satisfy the moment equilibrium equation or the statical moment equilibrium of the general differential shell element. Considering anticlockwise moments to be positive and ignoring the internal actions that have already vanished or have been found to be negligible, such as the bending moments mx, my, and the torsion moments tx, ty, as well as the outer plane shear forces qy and qx that have all been shown to be negligible or zero based on the thin shell assumption. The statical moment equilibrium equation about the z-axis implies that the internal in-plane shear force nxy is equal to the internal in-plane shear force nyx, which are therefore complementary shear forces or in-plane shear forces that can be recognized as complementary shears that are required to balance each other or be equal and opposite to each other in order to satisfy the rotational equilibrium of the general differential shell element about the z-axis. Summarizing the general state of forces, that have been established or derived mathematically based on the thin shell assumption and the hypothesis that a thin shell acts as a membrane, since the external loads are resisted primarily by membrane actions in a thin shell, that qualifies the necessary and sufficient condition for a thin shell, as expressed by equation 1, that the thickness of the thin shell is negligible in comparison to either of the two radii of curvature. The non-zero unknown internal actions that remain to be solved, or the non-zero internal actions that exist after the vanishing of the out of plane internal actions mx, my, tx, ty and qx, qy being reduced to 0, there are only 3 unknown internal actions that remain to exist, to be non-zero after the application of the thin shell assumption, which are the 3 in-plane internal actions nx and y, and either one of the 2 in-plane shear forces nxy or nyx, since the in-plane shear forces nxy and nyx have been established to be equal to each other. In other words, the thin shell assumption reduces the number of unknown internal actions or unknown variables that need to be solved from the consideration of statical equilibrium from 10 unknown variables, that is mx, my, tx, ty, qx, qy, to only 3 unknown internal actions, that is nx and y, and one of the 2 complementary shear forces nxy or nyx. Upon the application of the 3 moment equilibrium equations, that is sigma mx equal to 0, sigma my equal to 0, and sigma mz equal to 0. In conclusion, the application of the assumption of thin shell which allows the out of plane internal actions mx, my, tx, ty, qx, qy to be neglected. Simplifies or reduces the problem of determining the unknown internal actions in the general differential shell element presented in the earlier slides from 10 unknown internal actions, that is mx, my, tx, ty, Qx, Qy, as well as the in-plane internal actions Nx, Ny, Nxy, and Nyx to only three unknown internal actions which are remaining to be solved, that is Nx, Ny, and one of the two, Nxy or Nyx, the complementary shear forces. Since all other unknown internal actions have been shown to vanish or reduce to a negligible or a zero value by virtue of the thin shell assumption. And in order to solve for the remaining unknown internal actions numbering 3, that is the in-plane axial force Nx, the in-plane axial force Ny, and the in-plane shear force Nxy, we still have 3 remaining equations from the consideration of statical equilibrium, which are the 3 remaining force equilibrium equations: sigma fx equal to 0, sigma fy equal to 0, and sigma fz equal to 0. That is the 3 remaining statical equilibrium equations for the force equilibrium of the differential general shell element along the x, y, and z axis. Therefore, it may be interpreted that the solution of the unknown internal actions that remain to be solved or determined after the application of the thin shell assumption or the membrane theory of shells are only 3 in number, that is the in-plane axial force Nx, the in-plane axial force Ny, the in-plane shear force Nxy, and there are 3 equations from the consideration of statical equilibrium that remain to be used or have not been used till the present point in the above derivation, which are the 3 force equilibrium equations: sigma fx equal to 0, sigma fy equal to 0, sigma fz equal to 0 along the x, y, and z axis of the differential shell element. Thus, the problem has been considerably simplified, and the solution of the unknown internal actions that remain to be solved may be completed using equations of statical equilibrium that are not yet used. In other words, the solution of the remaining unknown internal actions that are nx and y and nxy may be achieved by applying the remaining statical equilibrium equations, that is the remaining statical force equilibrium equations along the x, y and z axis, which have not yet been used to solve for the remaining three unknown internal actions that have been found to be finite non-zero with an unknown magnitude. In conclusion, the mathematical proof of the hypothesis that the thin shell acts as a membrane has been formulated and presented in the current slide by applying the thin shell assumption to the three statical moment equilibrium equations for the general differential shell element presented in the earlier slides, resulting in zero values of the outer plane shear forces Qy and Qx based on the hypothesis that the flexural rigidity or bending stiffness of thin shell is negligible, or may be neglected or ignored as being almost equal to 0.